Okay, so we want to talk about BJT operating regimes because we need to get equations for the voltages and the currents of a BJT. And so we have to break it down into its different regimes. So here is the basic BJT, and it has three terminals. The emitter terminal, or the E, is the one with the arrow on it. The collector is the top of it, and the base is our primary control, and that's the one that goes into the flat section, perpendicular to the flat section. Okay, so we're going to be dealing with the NPN transistor. There's 4 regimes right here, but there's really only 3 regimes that we are going to work with. This one right here, the reverse active, we are not going to use. If you create some design that's in this state, you will get marked off because that's wrong. We're going to avoid that state because it doesn't operate as well as it does in the other states. Okay, so let's start with our forward active. So in the forward active regime, you see that basically the collector voltage is higher than the base voltage, which is higher than the emitter voltage. And this means that your base emitter junction right here is going to be forward biased because your base is higher than your emitter. Your base collector right here is going to be reverse biased because the base is less than the collector. So let's go over to LT Spice and look at this. So we want the collector to be our highest voltage and the emitter to be our lowest voltage, and then the base somewhere in between. So let's just come in here and make this 10 volts. And then we are just going to be turning this voltage on. So we're going to just sweep it. So we're going to sweep it from 0 to a volt. And we're just going to make a pulse. And simulate, edit. Okay, so we sweep this, and what we see here is your voltage increasing, and then what you see is, if we look at our current going through here, okay, what we need to do is we need this junction to be forward biased. Okay, so for this to be forward biased, let's go ahead and change this to be V of B. So you see that when I get up to about 0.7 volts, all of a sudden it starts to conduct current. So this regime right here is where, let's go back here, is actually in our cutoff. And so in this case, our base emitter junction is reverse biased. Well, it's still forward biased in our case, but it's really small. So if I look at the BJT data sheet, so here we're using the 2N3904. So here are our 2 cases. So this is our base emitter, and you see base emitter is about 0.65. We're going to use 0.7. So you see that if my voltage is less than about 0.7, it's basically in cutoff. So it doesn't have to be all the way reverse biased, it just has to be less than the turn on voltage of our diode, basically. So this regime right here is cutoff. This regime right here is active. Okay, so if my base emitter junction is below 0.7, it's in cutoff. If it's greater than that, then it's in saturation. It's in active. So then what is saturation? So let's go look at what saturation is. So saturation is where both of those junctions are forward biased. So let's go look at our data sheet. And so it says collector emitter. Okay, so rather than analyze it as the collector base being forward or reverse bias, they look from collector emitter rather than collector base. And so then this has a 0.2 voltage across there. So if the voltage across this point here goes less than 0.2, then that's in saturation. In this case, we're fixing this voltage at 10 volts, and so it never goes into saturation. So let's throw a resistor in there. And what the resistor is going to do is if I start to conduct current down here, let's move this down to here. Okay. So if I start to conduct current, then the voltage at this point is going to drop across that resistor, and this voltage here is going to get smaller and smaller. Okay, so now we plotted this current going down here as a function of this voltage right here. So in this point right here, you're in cutoff, but then you see it starts to go up until I get to some point right here, and in this point right here, it seems like it stays the same. So let's look at the voltage at this point. So eventually, you see I have the 10 volts across there. This is in cutoff. This is in active, and then right here my collector, my emitter is ground, so this is basically my collector emitter voltage, and it's dropping as I start to conduct current. Well, eventually there's no more that it can drop, and then this point here is basically 0. So if I look right here, you see it drops down to 23 millivolts. Now, any time that I'm less than about 0.2, you see this is really where we're transitioning into right. So we're going to use 0.2, 0.3. So this is really at the point where you transition into saturation. Okay, so this point's in saturation, this point's cut off, and then this small section is active. This section right here is where we want to use the transistor most of the time, because this is the region where it's going to be called linear, where we can make amplifiers and things like that. So this is my amplifying region. This is where we model it as an open switch, because right here there's no current conducting. There's no current conducting, it's an open switch. And over here, we call this a closed switch, and this is the